Hi there, I'm Wenchao, a software engineer at Conf. Today I'm so glad to have the opportunity to share with you some exciting updates and innovations of the Conf Gateway. Before that, let me spend some time to tell you a little bit more about our company and our products. Conf is a company that provides API gateway products and solutions. We have been focusing on helping our clients manage and secure their APIs effectively, empowering global companies to embrace an API-first approach. The Conf Gateway is an open-source, scalable, and high-performance API gateway product that provides features such as authentication, traffic control, HTTP transformation, logging, and monitoring. In addition to the open source gateway, Conf also provides enterprise solutions, which may offer advanced features and support for organizations with specific requirements. We also provide a cloud-native solution called Connect, which enables you to manage APIs across any cloud team from one place. Connect provides a hosted unified control plane to manage gateways and ingress controllers. This empowers your organization to reduce operational overhead, speed up time to the market, increase security, and achieve federated governance at scale. So in today's presentation, I will be focusing on Conf Gateway from several aspects. The presentation will be divided into 3 parts, each focusing on different aspects of our enhancements and innovations. First and foremost, I will be introducing the significant improvements we've made in some plugins and exploring the key innovations for some core components that are powering up the Conf Gateway. Following that, I will show you how we do our performance at Conf. In the third part, let's explore some skills in fine-tuning the performance for an enhanced user experience. Conf has hundreds of out-of-box plugins to address various use cases without introducing any platform complexity. This makes Conf flexible enough to boost developer productivity and ensure operational resilience. In today's talk, we will just have a quick look at the latest improvements in some widely used plugins. So let's start with the Prometheus plugin. As a commonly used cornerstone in modern monitoring system, Prometheus always plays a crucial role in Conf Gateway. While it can perform well in scenarios with a relatively small number of routes, we recognize the decline in performance as the number of routes increases substantially. So we took this as a challenge, and the followings are what we have worked out. As illustrated on this slide, we have already accelerated metrics scraping for the Prometheus plugin, and we have also implemented a reduction in high cardinality metrics. These enhancements eventually result in an improvement in the P99 latency, which means it now can run smoothly even in large-scale systems. 3 factors contribute to these improvements. Firstly, we've adopted the table pool for the creation of temporary tables, which optimize the process and mitigates the cost of excessive table creation during Prometheus scraping, so that we can avoid the performance hit of creating new tables all the time. Secondly, a few yield functions have been introduced in critical code sports, which allowed the Lua GIT compiler to release the control of CPU and give it to other request processing events rather than holding the CPU for too long time. This improves the responsiveness of the gateway quite a lot. Lastly, we've also replaced all the NYI functions involved in this plugin with those compatible with the Lua.git compiler, which completely harnesses the performance benefits of Lua VM. These changes collaboratively contribute to the performance boost. The following bar chart shows a comparison of the P99 latency between 3.3 and 3.4 version. We just need to pay attention on the red and the green columns. The red one stands for version 3.3 and the green one stands for version 3.4. Here we can see a significant enhancement of the 3.4 in the P99 latency. Now let's move on to the rate limiting plugin, which is a plugin for the purpose of traffic control. For this plugin, we've also got a notable increase both in P99 latency and RPS. The enhancement is mainly attributed to the introduction of a batch queue, which is a fundamental component newly introduced in 3.4, especially when the backend of the rate limiting counter is an external storage. With the help of this queue, there is no need to communicate with external storage for every single request. It just put data in this internal in-memory batch queue almost without any latency every time the counters are calculated. When the queue flushes these counters to external storage asynchronously, so it optimizes the method of communication between the plugin and external storage, particularly beneficial in high concurrency scenarios. We've also introduced a new configuration sync rate so that we can even decide the flush frequency. The graph below illustrates the test result we did compared to a Golang-based open source gateway. As we can see, the performance in P99 and the RPS is nearly twice as good as the competitor. Now that we have discussed the improvements in plugins, let's delve into the enhancements in some core components. To begin with our discussion about the core components, let's first focus on the router component, which plays a key role in route pattern matching. Why is there a need for improvement in the router? Well, given that users heavily depend on its flexibility and efficiency to configure their routing requirements effectively. The router stands out as the cornerstone of a gateway. Moreover, nearly every individual request should be checked by the router to determine if it matches with any API path, the config API path we've set. As traffic volume increases, the router becomes a critical focal point, and its performance emerges as a key factor. Since version 3.0, we introduced a new router implementation, which is called ATC router. The ATC router is a DSL-based approach and is written in Rust. The main reason for us to upgrade to a DSL-based approach is to enhance flexibility. The new router empowers users to set routes with expressions. Configuring routes using expressions allows for more flexibility and better performance without losing readability when dealing with complex or large configuration. Furthermore, we rewrite it in Rust, as Rust is not only generally quite efficient comparable to C language, providing high performance with low level control, but also is much safer than C in terms of its handling of memory. So it's ideal as a replacement for the language of choice for the development of a new module. Although it is never such an easy thing to rewrite a brand new module completely in Rust, because Rust is not a native supported language in operating. Several engineers invested a considerable amount of effort in this project. The results proved that everything was worthwhile. The new router can reduce root rebuild time when routes change. Meanwhile, it increases runtime performance when routing requests, and it reduces P99 latency from 1.5 seconds to 0.1 seconds, testing with 10,000 routes. Besides the rewritten of the routes, we've made two more optimizations for the logic of the router. Firstly, we optimize the route rebuild logic. Secondly, configuration conditional rebuild of the routes was introduced, which means the route builder becomes more intelligent. It can be conscious about if routes have been changed and if it needs a rebuild indeed. These optimizations also contribute to the final enhancement. The second core component that I want to share with you is the improvement in our approach to configuration management. In our previous iterations, we rely on a shared memory as the configuration storage, which is a kind of a native approach that provides node-level storage accessible across all worker processes. While this was effective in ensuring fast in-memory storage, we recognize the need for enhancement due to excessive memory consumption. Another concern is that shared memory is not a database-like storage. It does not support transactional operation. In some cases, this is an unacceptable reality because the inability to guarantee atomicity, which means we would need to use more code to ensure data consistency. This will increase the complexity of the code. From version 3.0, we handle configuration by introducing lmdb as the backend for Conf, which is an in-memory transactional database. By doing this, we've not only achieved a notable reduction in memory usage, but also unlocked the power of transactional storage. The benchmark readouts here also reveals that lmdb significantly improves RPS during rebuilds with a constant config push. What's more, we observed a remarkable 50% to 70% additional drop in rebuild time, particularly noticeable in cases with a large number of workers. Cone Gateway is based on an nginx and OpenResty. It has a unique master worker architecture for efficient CPU usage by forking multiple worker processes, and it faces information sharing challenges across workers due to the isolated nature of worker processes. To address the communication needs between workers, especially for tasks like router rebuilding and health checking, Cone designed an event propagation mechanism. Previously, the event component we implemented relied on shared memory. Though this approach was effectively, it had drawbacks, such as high log overhead. Accessing a single shared memory requires a log to avoid race conditions and keep consistency. This leads to high overhead when there are numerous workers, which is considered as a kind of inefficiency. Another concern is the size of the shared memory. It should be decided and allocated in advance when nginx starts, and it cannot be changed during the runtime. It means that regardless of whether this part of shared memory is fully utilized, it has already been allocated. To enhance efficiency and avoid risks, we upgraded to a new event lib called Lua Resty Events. The new event library operates as a classic publish subscribe model and is implemented by a pure Lua code, eliminating the need of shared memory. We did tests to compare the two event libraries. We designed two test cases to do this. One is to post 1,000 events per 5 milliseconds. The other is to post 10,000 events per 100 milliseconds. The benchmark here reveals that under the low pressure condition, the two libraries have nearly the same performance in the RPS, while the new library wins when the workload increases. Considering that performance is essential for commercial products to deliver an excellent user experience, we carefully designed a testing system and a set of statistical methods. Here is the infrastructure of the testing system. Two bare metals have been set up. One works as a load generator, and the other is used for the deployment of Cone. We even bind different components, the nginx upstreams and the Cone gateway, to different groups of CPU, trying to get rid of CPU competition. And we connect these two buried metals with a private network to fully utilize the network bandwidth. And we even put upstream and Conf gateway on the loopback to give WRK more bandwidth. Here are the methods we used to check all the key metrics: RPS, latency, and memory usage. And this graph shows how we check the decrease in metrics. We compare two groups of sample results to see if there's a significant difference. We do the test every day, and if the difference happens, the test is considered a failure, and we will get a notification about it. Among two groups of results, one comes from the test result, which is a post-release perf test being carried out for a new version release, and the results will be persisted in storage. The other one is tracked every day and persists in the same storage in case we need to review it. The charts illustrated on this slide tend to show you the effect of our methods. As you can see, it is easy to find out the variations between the test cases. When the difference is found, a perf will be run to collect the perf data and generate the flame graph so that we can have an insight into details. From the flame graph, we can generally find out the problematic function. And after we made changes in our code to fix the issue, we run the perf again to confirm the issue has gone. This is just an example to show you how we do performance. In the last part of today's presentation, let's learn some practical insights into tuning the performance. Sometimes performance tuning can be intricate, and today I will just talk about some common and fundamental strategies as examples. For more in-depth information, please explore the technical blogs on Conf official website. So Conf as an API gateway, it comes out of box being well tuned for proxying traffic. However, there are some cases where Conf is used for processing requests with large payload. So let's explore this case first. Conf utilizes a request buffer to hold the payload, and when the payload exceeds the buffer size, the nginx resorts to use the disk to buffer the request. This can avoid excessive memory usage, preventing potential memory shortages that could lead to extensive disk operations. Such disk operations can be costly and may block nginx event loop, resulting in performance degradation. To mitigate this, a simple solution is to increase the buffer size, defaulted at 8,000. As illustrated in this graph, the larger the buffer size is, the better performance we can get. Another case arises when Conf receives responses from upstream with large payloads. Similar to the previous case, a buffer is in place for catching response bodies. The same principle holds true as demonstrated in this graph. Although buffering can increase performance, some cases are not suitable to enable it, including real-time cases, long-term connection, or streaming transmission or streaming processing. And also, we should not enable it when memory of the environment is limited. Okay, I think that's almost everything I would like to cover in today's presentation. Due to the limitations of the slides, some topics may not have been fully discussed. If you have any question, please feel free to reach out to me. I'll be glad to help you. Thank you.